I'm going to shift gears here a bit now. We're still in the same unit. We're still going to talk about forces over the next few days, but we're not going to talk about forces nearly as much or nearly as directly as we have been over the last several weeks. We're going to focus on an area of dynamics now that we call energy. Energy, if you remember from Science 10, is what we define as the ability to do work. It doesn't mean that we're doing work right now. It means that it's the ability to do work. Okay, if I drop a pen towards the ground here, something's being done right now. As it moves, something's being done. It displaces air. It moves. It can damage the floor. It can damage the pen when it hits. Work is being done. But if I hold the pen right here, we're not doing any work. But we're still saying that this pen has energy, not because it's doing work right now, but because it does have the ability to do work. It's got stored energy right now. We call it gravitational potential energy. All I have to do is move my hand, and all of a sudden the pen starts falling. Okay? It's not doing work as it's sitting there at a height, but it has the ability to do work. If I move my hand, it falls and starts doing work. We're going to define energy as the ability to do work, and we're going to distinguish between two types of energy that I kind of just alluded to a minute ago. The one type of energy that's actually doing work that we call kinetic, and the other kind of energy that's just kind of waiting to do work, just kind of sitting in the wings, waiting to do something useful that we call potential energy. Now, if kinetic energy is doing work right now, then it must be because something's moving. So we're going to say that kinetic energy is the energy of motion. The pen, when it was falling, was doing work because it was moving. It had kinetic energy. As opposed to the pen, when it was just being held a certain distance above the floor, it had the ability to do work. It had the ability to start moving, but it wasn't moving yet. The energy that it possessed at that point was stored. It was stored energy, just waiting in the wings to start causing this object to start moving. We call that potential energy. Now, kinetic energy, we don't usually distinguish between types of kinetic energy. If something is moving, we say that it has kinetic energy. A car is moving, it has kinetic energy. A planet is moving, it has kinetic energy. A subatomic particle is moving, it has kinetic energy. We don't usually distinguish between different types of kinetic energy. But potential energy, we do. Okay, there's lots of different types of potential energy that we distinguish between. Okay, the first type, or one type, is the type that we just alluded to, gravitational potential energy. If I can spell it. You might think of another kind of energy that's stored. It's not doing any work right now, but has the potential to do work. Maybe down the road, if something gets harnessed, maybe all of a sudden it can cause something to start moving. Yeah. Chemical potential energy, perfect example. Yeah, we're not going to talk about chemical potential energy too much in physics. That's more of a chemistry thing. Okay, but certainly it's still a type of energy that's sitting there, waiting in the wings, just waiting to get something moving. The gasoline in your car has energy in it. It's chemical potential energy. It's not doing anything right now, but as soon as you burn that gasoline, you can cause your car to start moving, right? Generates thermal energy, which ends up causing this, causing the piston to move back and forth and causing your wheels to move. So in the end, the gasoline as it sits in your tank as you're waiting to turn on your car is not doing anything right now, but it does have the ability to do work. It has the ability to get your car moving, to give your car kinetic energy. Okay, in our bodies right now, I'm walking around the classroom right now. Okay, as I stand here, I have chemical potential energy stored in my body. Okay, that chemical potential energy has the ability to do work. It's not really doing anything right now, but it has the ability to do work. If I start moving, oh wait, oh yeah, okay, if I'm moving, I must have gotten energy from that kinetic energy from somewhere. Well, it came from the chemical potential energy in my body. There's chemical potential energy stored in the food that you eat, right? That's ultimately what allows us to walk around and to talk, the chemical potential energy stored in the food. Anything else? Energy that's not doing anything right now, but has the ability to get something moving. If you were in maybe the southern United States, you might be thinking of this. Even in Okotoks, actually, there's some of this, like Okotoks is becoming a fairly big community for this. You know that we get more sunlight in Okotoks than they do pretty much anywhere in North America. You wouldn't think it when it's minus 30 degrees in the wintertime, but we do get a lot of sunlight in Okotoks. Therefore, Okotoks is actually a pretty good place to actually harness solar energy. It's not doing anything, but it has the ability to do something. If you were in, say, North Korea, you might be thinking about this type of energy. What is it? Nuclear. Now, there's lots more types of potential energy as well. These are the kinds that kind of came to mind here today. The kind that we're going to focus on in this unit is gravitational potential energy. Sorry, there is one more type that I wanted to address here. We're not going to deal with it that much in this unit, but we will talk about it quite a bit more in a unit down the road. It's what we call spring or elastic potential energy. If you stretch a spring out, okay, you can let it go and it can do something, right? If you stretch an elastic out, right? Stretch that elastic out on your finger, let it go, and it flies through the air and hits somebody, right? It can do something. So it's energy that's stored in the stretched or squished spring or elastic. We'll talk about that quite a bit more when we get to our last unit. This unit, we're going to focus on kinetic energy and gravitational potential energy. Let's go back to the kinetic energy for a moment here. Kinetic energy, energy of motion. Energy of motion, what's it dependent upon? What variables do you think might appear in the equation to describe kinetic energy if it's energy of motion? What variables are going to affect how much kinetic energy something has? One of them is obvious. Like, really obvious. It's staring you in the face. Kinetic energy is the energy of motion. What affects how much kinetic energy something has? David? Looks like you're ready to give me an answer there. Well, I mean, that can affect, the variable that I'm thinking of can be affected by that. Yeah, speed, not velocity, because kinetic energy ends up being a scalar, actually. In fact, all energy is a scalar. Kinetic energy, potential energy, whatever is a scalar. So we're not talking about velocity, we're talking about speed. Okay, kinetic energy is energy of motion. It's dependent upon how fast something's moving. But it's also dependent upon the mass of the object. So the equation for kinetic energy that we're going to use looks like this. EK is equal to 1/2 mv squared. Does that ring a bell? You guys have seen that before, right? 1/2 of the mass times the speed squared. What units do you think we'd use for mass here? What units do we always use for mass? It's going to be kilograms, right? What about speed? Always going to be meters per second. So remember, if you've got kilometers per hour, make sure you convert it to meters per second. You got grams or milligrams, make sure you convert it to kilograms. What are the units for energy? Somebody said it? Joules, yeah. You could actually say, just off to the side here for a second, you could actually say 1/2 mv squared, kilograms times meters per second, meters squared per second squared, right? Mass times v squared. And that's a set of units you could use for energy, but that's exactly the same thing as a joule. And a joule is a lot easier to write than a kilogram meter squared per second squared. So let's just go with the J. Let's just go with the joules. Kinetic energy, energy of motion, 1 FmV squared. Hey, here's a quick question. What affects the kinetic energy of an object more? Okay, what matters more? How heavy the object is or how fast the object is moving? They make bullets now, these high velocity bullets. They want these bullets to have more kinetic energy because these high kinetic energy bullets do more damage, right? So what have they done? They've made them lighter. Wait a sec, isn't that going to give it less kinetic energy? What effect does making it lighter have? It makes it go faster. So if you cut the mass in half, then the velocity is going to double. Well, so what? Okay, you're increasing one, you're decreasing the other. Big deal, right? That's not going to affect anything, is it? But wait a second, it is. If you cut the mass in half, that doubles the speed of the bullet. The speed of the bullet matters more than the mass does. So yeah, you lose a little bit of kinetic energy by cutting the mass in half, but you gain a lot more kinetic energy than you lose by doubling the speed. How come? Go ahead. Because the speed is squared. Anything that's squared has a bigger effect than anything that's not squared. All right, let's go to gravitational potential energy here. You guys remember the equation from that from Science 10? Gravitational potential energy, EP. EP, by the way, is a symbol for any type of potential energy. Gravitational, chemical, elastic. We're going to use it in the context of gravitational, though. This board marker has gravitational potential energy. What affects how much gravitational potential energy it has? Tell me something that determines how much potential energy it has. Yep, the mass. Yeah, the heavier it is, the more potential energy it has. I'm holding it. If it's really, really heavy, it's going to be harder for me to hold. It's going to be easier for it to start falling and start actually doing some work, converting it to kinetic energy. What else? The height. Yeah, the height. The higher it is, the more ability it has to do work. I drop it from this height, it's going to be moving at a certain speed when it hits the ground. If I drop it from this height, it's going to be moving a lot faster when it hits the ground. It's going to be doing more work. So the height is going to affect it as well. There's one other thing that affects it, though. Yep, gravity. If you're on the moon and you drop something, it's not going to be falling nearly as fast when it hits the ground as on Earth. Gravity affects it as well. M is mass, it's measured in kilograms. G is gravity, and it's going to be, for the most part, 9.81 meters per second squared, although that number could change. H is going to be the height, of course, and it's going to be measured in meters. EP, potential energy, well, we could say that, take a look at this, M is kilograms, G is meters per second squared, H is meters. Look at that. What do we get? Kilograms meters squared per second squared, the same as we got for kinetic energy. Well, what's an easier way to write that? Let's call it a joule again. Potential energy, kinetic energy, any kind of energy can be measured in joules. Spring or elastic potential energy that we'll do in more detail in our last unit, still going to be joules. Here's a question for you. It says, on a highway, a car of mass, this is chapter 6, by the way, if you didn't notice. Okay, on a highway, a car of mass, 1,200 kilograms, traveling at 20 meters per second, has a kinetic energy equal to a loaded van of mass, 4,800 kilograms. What's the speed of the van? You know what? That's a hard question to start off with. And that's kind of a nasty one to give you for the first question on energy. But you know what? You guys are smart now. You guys can handle this. You guys are way smarter than you were a couple months ago. What do we know about this? Well, we're clearly dealing with kinetic energy. We're clearly dealing with two objects. And we're clearly dealing with two objects that have equal kinetic energy. That's a big deal. They have equal kinetic energy. They're telling me right now what to do. They're telling me exactly what to do. They're saying, get the kinetic energy of the car. Actually, let's write down some givens here. Let's say the mass of the car is 1,200 kilograms. Let's say the speed of the car is 20 meters per second. Let's say the van has a mass of 4,800 kilograms, and the speed of the van is whatever. They're telling me the kinetic energy is the same, so let's get the kinetic energy of the car, and then let's set that equal to, because they're telling me it's equal to the kinetic energy of the van. One half of 1,200 times 20 squared. I think it's 240,000 joules. Not a final answer, so let's not round it yet. But we know the kinetic energy of the van is exactly the same, so let's say EK van, 1/2 mv squared. Rearrange this to solve for V. How do we do that? How do we rearrange that to solve for V? Well, we're going to take the 1/2 m over dividing. And then we're going to square root it. We know the kinetic energy because it's the same kinetic energy as the car had, 240,000 joules. Divided by 1/2 of the mass of 4,800 kilograms. And then we square root that. We end up getting 10 meters per second. Remember what we said a few minutes ago about which has more of an effect? Speed. Speed is squared. Look at what we've done here. We've quadrupled the mass. If we're going to have the same kinetic energy, then the speed's going to have to go down. But notice the speed only went down by a factor of 2. The kinetic energy, sorry, the mass went up by a factor of 4. So V is a bigger, V is more important than M. All right. Besides your quiz tomorrow on inclined planes, this is your homework. Page 303, questions number 1 to 3.